Hello, ladies and gents, and welcome to your optional polar graph, polar equation notes. We're going to talk about how to test if a polar graph will have symmetry prior to actually graphing it. The benefit of performing these symmetry tests is that if you know the type of symmetry a graph is going to have before you actually graph it, you can plug fewer points in. So your table is going to be a lot shorter. You don't have to do everything all the way around the unit circle, all those special angles. And so you can create a smaller table, you create your graph faster, and really you get to that final product a whole lot quicker. Now the symmetry tests do use some of the identities that are on your identity sheet. So if you have your identity sheet at home, go ahead and pause this and pull out that identity sheet. If you don't have your identity sheet at home, the identity sheets are linked under the Chapter 9 and Chapter 10 modules, but I will also be handwriting onto the notes. I will also handwrite the important identities you will need in order to perform these symmetry tests for polar graphs. So if you want the notes in advance, if you printed out the notes 14.6 from the last video, it is exactly the same as you see on the screen. We are going to fill in and continue from where we talked about the types of symmetry right here, the different names for the x-axis, y-axis, and the origin. They're no longer called that since we're in polar graphing mode. We are actually going to fill in right underneath here all that blank stuff that we didn't fill in before. So if you need those notes again, or you want them as a guide, they are linked. They were linked right here before this video. So without further ado, I'm going to flip around my notes. Got really excited. The Amazon delivery person delivered me some new colored pens so I can veer off of just using purple. It makes me really excited. I don't know how excited that makes the rest of you. So anyway, before we really jump into it, let's do just a very, very brief review. The y-axis no longer will be referred to as the y-axis. The y-axis in the polar in polar coordinates is referred to as the line theta equals pi over 2. Makes sense because pi over 2 is this angle right here. The x-axis is no longer called the x-axis, but it is called the polar axis. And the origin, not called the origin, it is now called the pole. Now, when we did talk about these in the last notes, I did briefly talk about the other set of coordinates and what reflecting would mean. This is where the extra set of coordinates is going to become important. So first things first, I actually think it's easier to come up with these coordinates starting on the right-hand side. We said if I had a random point r theta up here in the first quadrant, if I had symmetry with respect to the pole, then we also have this point negative r theta. Now I know that this is the correct way of describing this random point right here, because we know that a negative r indicates that I slid back through the origin. So if I had r theta just covering up that negative, I would be right here, but having that negative r means I'm going to slide back through the origin, which puts me right there. Hence the negative r positive theta. Symmetry with respect to the polar axis, we said again, if I had this arbitrary point r theta, then this point would be r negative theta. The reason that works, well, it makes sense the r, I have not changed my distance from the origin. Remember what a negative in front of a theta value means. It means rather than going forwards, theta radians or degrees, I'm going to go backwards. Backwards around the unit circle would be in this clockwise direction. So let's say, for instance, because I did plot this at 60 degrees, if theta was 60 degrees, I would be here. But a negative 60 degrees means I'm going to rotate backwards in a clockwise direction 60 degrees. Hence the point r negative theta. Last but not least, with symmetry with respect to the line theta equals pi over 2, if I have r theta, we said this point is negative r negative theta. Now, that's kind of a lot to think about. So if this is r theta, then let's go one at a time. Negative, well, we'll go it this way. If I had positive r negative theta, that would put me in the same place as this guy, which is right here. I've gone backwards, let's say 60 degrees or whatever the angle happens to be. Adding in that negative r means now that I've gone backwards my theta degrees or theta radians, I'm going to slide back through the origin, which is why I land up here, but it does demonstrate that symmetry with respect to the line theta equals pi over 2. Like I mentioned, these extra points are now going to become important. So how do we test for symmetry before we graph? Well, there's 3 types of symmetry that could be exhibited. So there are 3 symmetry tests. If we want to test for symmetry with respect to the line theta equals pi over 2, then in our original equation, we are going to replace all of our r's and thetas with negative r or negative theta. Negative r, negative theta. And whoops, here is why. Because if I have symmetry with respect to the line theta equals pi over 2, then not only do I have the point r theta, I have the point negative r negative theta. So I'm going to replace with this extra set of points. Now, side note, if what I'm going to write in pink on here is going to be enough for extra credit and for the purposes we're doing now. There is actually a second variation of every single symmetry test, which would utilize either co-function identities or sum and difference identities. You could technically do it either way. I am not going to walk through any of those variations. If you would like to see them, please either shoot me an email or request a Google Meet, and I would be happy to go through those. Again, I'm only going to worry about the tests in the pink, because if I throw too many tests at you, then it could not be pretty. But the other option is to test, rather than negative r negative theta, would be to replace it with r pi minus theta. And again, I'm only going to worry about the ones in the pink because I don't want to throw too many tests at anyone. So that would be our symmetry test for the line theta equals pi over 2. If we want to test for symmetry with respect to the polar axis, then we are going to replace r theta. Probably guessed what we're going to replace it with. We are going to replace r theta with r negative theta. Now, again, if you want to get really crazy and you want to try a second variation of the test, again, I am not going to go through it. It would be negative r pi minus theta. And last but not least, if we want to test for symmetry with respect to the pole, then we would replace r theta with negative r theta. And for those of you who really want to try a second variation of the test, it would be r pi plus theta. Again, I'm going to focus on what is in green here, not what is in green, but what is in pink. Too many symmetry tests get a little crazy. Okay, so how does this all fit together? Well, let's say we want to test for symmetry, or we want to graph the polar equation 1 minus 2 sine theta. 1 minus 2 sine theta. Okay. First thing I'm going to do, I'm going to run through all 3. Because let's say I have no idea what to expect. I know we have page 899 in our book that shows us the basic shapes of graphs, but we also know that those could all rotate. So symmetry, you never really know. So I am first going to test for symmetry with respect to theta equals pi over 2. So in order for me to do that, I am going to go through my equation and I am going to replace all the r's and the thetas with negative r, negative theta. So I am going to replace my r with negative r and my theta with negative theta. So how do I know if we have symmetry? If we have symmetry, by replacing the r's and thetas with the appropriate substitution, if I simplify my equation and I can get back to the original, that signifies to me that our graph will exhibit whichever type of symmetry we happen to be testing. So again, if I make the appropriate replacement, and I'm again only going to focus in the pink, if you want to try the green, that would use co-function identities, or not co-function identities, it would really only be sum and difference identities. It would use sum and difference identities. You absolutely 100% may do that, but I am going to just focus on the pink. But if I make those replacements and I simplify my equation, getting me back to the original, that tells me that I exhibit the type of symmetry that I happen to be testing for. So how do I simplify this? Now, dealing with a negative coefficient is one thing. Dealing with a negative coefficient within a trig function is another. And here is where that next set of needed identities comes into play. If you happen to be looking at your identity sheet, we are going to be focusing on the even and odd identities. We are going to be focusing on the even and odd identities. Now, for our purposes, we really only need the sine and cosine even and odd identities. We're not really going to be dealing with the other trig functions. So quick blast from the past. Back in Algebra 2 and at the beginning of the year when we talked about the basics of functions, we talked about even and odd functions and the types of symmetry those happen to exhibit. We talked about how odd functions exhibit origin symmetry. Remember, those O's go together, and even functions exhibit y-axis symmetry. When we talked about even and odd identities, there was no x-axis symmetry because that would not be a function. Now, you do notice that none of these polar graphs really, most polar graphs, I should say, are not functions. They do not pass the vertical line test. So that should be in the back of your mind. So how does this all play together? Well, I'm going to give you the kind of the quick-ish version, the best version I can via a video, but I am just copying down what is on your identity sheet. And then again, we'll talk briefly about what this means and what this says. Okay. So let's first talk about the graph of sine, just the graph of the sine function. And we're going to talk about the graph of cosine. There's my theta or x-axis and my y-axis. If you remember, sine looks like an S curve, cosine looks like a C. So the graph of sine looks something like this, and I am going to continue it the other direction. Sine does not have y-axis symmetry. This point does not exist as a reflection on the y-axis. Sine does not have x-axis symmetry because it's a trig function that wouldn't pass, again, x-axis symmetry, the vertical line test, but sine does exhibit symmetry with respect to the origin. Therefore, sine happens to be an odd function. Sine is an odd function. Well, what does it mean to be odd? If you remember, to be odd, it means if I have a point up here, arbitrarily xy, odd means I also have the point negative x, negative y. In other words, for any function that is odd, I'm going to make this a little closer up, for any function that is odd, if I take my equation, and my original function would have been the sine of x. If I take the sine of x and I plug in the opposite input, that's what that negative in front of the x signifies. If I plug in the opposite input, then I get the opposite output. So for sine, when I plug in the opposite input, I get out the opposite output. On the flip side, we have cosine. I'll use a different color here. Cosine is that C graph, and I'm going to extend it in both directions. And cosine, as we can see, has symmetry with respect to the y-axis. That means then that cosine happens to be an even function. And on the graph, that means if I have the point xy, I also have the point negative xy. And I realize it's really, really hard to read. I will take a picture. Sorry, I need to work on writing larger when I do these videos. So what that means, having the point xy and negative xy, it means for our function cosine of x, if I plug in the opposite input, then I'm going to get the same output. So if I had taken the cosine of 45, that's the same as the cosine of negative 45. My output in both cases is y. So for cosine, when I plug in the opposite input, I get the same output had I plugged in the positive input. So the cosine of negative 30 is the same as the cosine of positive 30. These even and odd identities are going to help us when we make these substitutions, testing for symmetry with respect to theta equals pi over 2, the polar axis and the pole. So going back to the test that we had been performing, we did our substitutions to test for symmetry with respect to theta equals pi over 2. We plugged in negative r, we plugged in negative theta. So simplifying, there's no test for simplifying negative r. That's like a coefficient of -1. We can deal with that later. But let's focus on this. Sine, we know, is an odd function. Sine being an odd function means when I plug in a negative input, I'm going to get the opposite output. or sine being an odd function, when I plug in a negative angle, I am going to get the opposite of my function out. So I can simplify this part right here to be negative sine of theta by using the, in this case, odd identity for sine. Bringing down the rest of my function, I still have a 2. So negative times 2, I can slide that 2 right in here as a negative 2. And I had a negative already. That is not the negative from my function. 1 equals negative r. Simplifying further, double negative gives me 1 plus 2 sine theta. And again, my goal is to be able to simplify to a point where I get back to my original function. If I can do that, then I can guarantee that I will have this type of symmetry. Well, I've gotten this far. This is a negative. This is a positive. I still have this negative here. Now, some of you may be saying, well, divide everything by -1. That's going to make r positive and turn this back to a negative. That is true. If I divide everything by -1, I will get r, and I will end up with a -2 sine theta. But keep in mind, I have 2 different terms over here. So I would also have to divide the 1 by -1, which would turn this to a -1. So what this is telling me is I can't manipulate this equation after the substitution to get back to match the original. So I cannot guarantee that I will have symmetry with respect to the line theta equals pi over 2. Therefore, I fail that version of the symmetry test. Side note, if you want to try any of these symmetry tests in green using the sum and difference identities, feel free. You could potentially pass them, but we're only going to deal with one variation that is sufficient. If you are one of those who might be going into calculus later on, then maybe try the other ones. I think you will at some point get back into polar coordinates in calculus. So failed theta equals pi over 2. Now we're going to try for the polar axis. So we are going to try our polar axis test. And the polar axis test says replace r theta with r negative theta. So r and negative theta. Now, using the even and odd functions, we know how that negative theta is going to simplify. A negative theta, plugging in an opposite input for sine, gives me an opposite output because we are odd. So this becomes negative sine theta. Bringing down that 2, we're going to leave it as a coefficient. And I'm going to bring down the 1 minus. And simplifying further, 2 negatives make a positive. And we can, again, pretty quickly see that there's no way I'm going to make this match my original function. Therefore, we fail the polar axis test. Okay, so then let's try the last one. Symmetry with respect to the pole. Well, symmetry with respect to the pole, I'm going to replace r theta with negative r positive theta. So r theta with negative r positive theta. In this case, I don't need to apply any of the even odd function test because I have not changed my angle input here. Dealing with this negative r, I could try dividing everything by -1. And I get r equals -1 plus 2 sine theta. And again, I can see not going to get back to where I was. So I am going to fail this test as well. So now you may be thinking, Mrs. P, what was the point? I just tested for symmetry. We just tested for symmetry and we failed every single test. So here's some good news. Good news about the symmetry tests. And I will do another example. You'll see this shortly. If I pass a test, graphing means I can plug in far fewer points. But at the same time, I can fail a symmetry test, and a failed symmetry test does not mean that there's no symmetry. It just means you failed the symmetry tests. So a failed symmetry test, does not mean no symmetry. It just means that you failed the symmetry test. You can fail every single symmetry test and still have symmetry. It's just that passing a symmetry test could make your life easier. So if I used my graphing calculator to actually graph 1 minus 2 sine theta, and we have a lemicon with an inner loop, and you can easily see on that graph that we have symmetry with respect to the line theta equals pi over 2, yet we happen to fail that test. Again, a failed symmetry test does not mean no symmetry. It just means your life could be made easier had we actually passed it. So you may be saying, can we do one where we actually pass the symmetry test? I say yes, let's go ahead and do that. So we are actually going to look at, let's go with, let's see if I have any other. Okay, you know what? Let's go. We're going to redo. We already graphed this one. 1 minus cosine theta. I wanted to throw one in. Did I use cosine anywhere else? Yeah, we'll go with this one. 1 minus cosine theta. And we already graphed it. We already know that it has symmetry with respect to the polar axis, but we are going to see what happens if we actually apply those symmetry tests. So I am going to recopy down my equation, and we are going to start our symmetry tests. Whoops, throwing some markers over here. So first symmetry test, theta equals pi over 2. Now again, we already know that we should fail this one. We better fail this one because we don't have it. Pretend for a moment that we've never seen this graph. So the symmetry test for theta equals pi over 2. Theta equals pi over 2. We're going to replace r theta with negative r negative theta. So I'm going to replace with negative r negative theta. Now, we did replace that theta with negative theta, which means we are going to need the even-odd identities to simplify the cosine of negative theta. Now, if you remember, cosine is an even identity, meaning when you plug in the opposite input, you should get that same positive output. So again, right here, even-odd identities, if I plug in a negative angle, I am going to get that same positive output. It's like that negative completely disappears. So I know that cosine of negative theta right here simplifies to cosine of just positive theta, bringing down everything else. Now, while this right side matches my original, that left side does not. And even if I divide off everything by -1, that would fix my left side and give me that positive r, but it would turn my right side into the opposite of what we want. So I'm going to say, as we expected, that this is a fail on the symmetry test for theta equals pi over 2. So next symmetry test, we are going to go with symmetry with respect to the polar axis. We are going to replace r theta with r negative theta. R negative theta for the polar axis test. R negative theta. Okay, so even and odd identities. Cosine again. Cosine is even. So when I plug in the opposite input, I get the same positive output, bringing down everything else. And take a look at that original equation after I applied and simplified our substitutions for the symmetry test. They match, which means we pass. Yay, we passed this symmetry test. Now, does that mean we get to stop and we don't have to test for symmetry with respect to the pole? The answer is no, because if you look through the graphs that we created, you could exhibit more than one type of symmetry. For example, our rose curve that we created in the last set of notes actually has all 3 types of symmetry. If we exhibit all 3, that makes your life even easier than you thought it could be with passing one. If I know that I pass all 3 symmetry tests, then I actually only have to plug in first quadrant angles, and then symmetry with respect to theta equals pi over 2 would flip me here. With respect to the polar axis would flip those coordinates here, and with respect to the pole would flip me here. So could you pass more than one symmetry test? Absolutely yes. So So yes, you need to test all three. Yes, you need to test all three. So symmetry with respect to the pole, we are going to replace r theta with negative r theta. We're going to place r theta with negative r theta. Now, Mrs. P, do I have to test for all three if I know, I can just see that that it's not going to pass? For the purpose of the extra credit in the project, then yes, I still want to see all three. So here we go. Don't need to apply even odd identities because we didn't plug in a negative angle. I just have this negative r here, trying to make that negative r positive so that it matches my original equation. I'm going to have to divide every term on the right side by -1. And similar to the theta equals pi over 2 test, it's going to flip the right side, even though it makes that r positive, and we are going to fail the symmetry test for symmetry with respect to the pole. Okay, so again, how would this have made our life easier? Had we done this prior to actually graphing this lemacon cardioid. Now we're still going to use the values of A and B to predict the shape, because that again helps us with connecting the dots. But knowing that we have symmetry with respect to the polar axis, remember the polar axis is, I guess you could say, similar to the x-axis. This means that when we are graphing, having symmetry with respect to the polar axis, then I only need to plug in quadrant 1 angles and quadrant 2 angles, and then I can take those points that I create and reflect them over the axis. So in creating this graph, I really would have only had to, there's my quadrant 1 angles. I'll call this Q1. My quadrant 2 angles, I would go through pi. Quadrant 2 angles, and I should notice that quadrant 1 reflects into 4 and quadrant 2 reflects into 3. So if I look at what was in my table, quadrant 3 actually is a reflection of quadrant 2, and quadrant 1 and 4 angles are a reflection of one another. So the symmetry test in advance, if you pass at least one of them, means the table that you create in order to create the graph can be that much smaller, because you can take the coordinates that you get from one set of plugging in angles, and you can just simply reflect that point in the correct direction based on the symmetry test that you passed. So hopefully that makes sense to many of you, all of you really, that are watching this, and hopefully that makes your polar graphing project a little bit easier. Hopefully you passed some symmetry tests. Also means you get some extra credit if you satisfactorily apply those tests for your polar project. And again, I did show in there in, what was it, green, the other variation of the symmetry tests. If you have any questions about those, feel free to ask. If you are feeling really, really brave and you want to try those extra symmetry tests using sum and difference identities on the project, you are more than welcome to. Any questions, again, please ask, and I will see you all soon.